Welcome back here. So we're doing the last half of this review package that we have here. Starting dynamics, moving on to like circular motion, energy, a little bit simple harmonic motion. You notice that this review package doesn't have any waves in it. That's okay. That's the most recent thing we did. Just, I don't know, just review some of the stuff we did. That needs to be fine there. All right, so the first few things here, what's really important is that you should know your Newton's three laws, like not necessarily like the wording of them, but their application. Like an object at rest will remain at rest or a constant velocity, right? Essentially, those two things are the same, but that means there's no acceleration unless they're acted on by an unbalanced force. So they're just going to just have a constant velocity of like zero or something, unless it's pushed on by something from the external, from the outside world, essentially. The next one here. I really don't like the wording of this little package here, but the F is equal to MA formula, which is probably better if it was A is equal to F over M formula. That's what's on the formula sheet. Where F net, the net force, the acceleration is directly proportional to the net force and inversely proportional to the mass of the object. All right, so I'm actually going to just change the wording right now. Probably save this later. All right, so the net force there. And then the action-reaction law. For every action, there's an equal and opposite reaction, but remember there has to be two objects. So again, this wording is a little bit dumbed down a little bit. Remember how it usually works out. You're going to have object A pushes onto object B, and object B pushes back onto object A with equal, a force of equal magnitude but opposite direction. All right, so that's a little bit more wordy way of saying the same thing of the action-reaction law. Right. A few things here, net weight. So this here, remember, true weight is equal to, let's put that word in there, true weight is equal to your Fg times, or Fg, which is mass times gravity, the gravitational field strength, of wherever you are, right? So your true weight can change. It's dependent on the gravitational field strength that you're in. On Earth, it's 9.81 newtons per kilogram, but it could be something else on a different moon, like the moon might be 1.6 newtons per kilogram. Mars is in the 3s newtons per kilogram. Venus is around the same as us, but way hotter, so you don't want to go live there. Then you got the normal force. Remember the normal force. The normal force is like your apparent weight. I'm going to put that in there too. So that's your apparent weight. It's what you feel if you're a person, like if you're in an elevator or something, or in a roller coaster. That's what you're feeling. You're feeling that pushback from your seat, pushback from the floor, pushback from whatever. Right? That apparent weight, your normal weight, or your normal force. Yeah. That's the Fn in most of our pictures. On a horizontal surface, just got to remember that they balance each other out. Most of the time, it really depends on what other forces are in that direction too. But the normal force kind of balances out all the other forces and makes sure it ends up being zero. As long as you're accelerating horizontally and not up and down, then your F net, or your normal force, is just to make sure that that's true. On an incline, your normal force is equal to Fg cos theta. Again, not necessarily all the time. Most of the time it is true. All right. Then you got applied force. Just we call it Fa. Here's some situations you have here. So you can see in the first situation here, the normal force here, if I can actually get that arrow, should be smaller than this, right? And the reason it should be smaller than this, I don't know if we can actually get it to be smaller without, there we go, oh no, without gripping onto one of those stupid little points on the thing. The reason it should be smaller, okay, is because there is an F applied at an angle here. So everything in the y direction should be balanced out. So you may not need as much normal force for that to be true. Gravity is a constant, right? So that's just a constant thing. I should probably put on the end of this little shape here a dot at the end of it, right here. All right. So the Fg is a nice constant thing. The F applied to here and the Fn, they're both going upwards. So those two vertical pieces should balance out the gravity. That's why the Fn might be a bit smaller here. all these pictures are kind of drawn incorrectly too. It's like I should probably fix these. I know they're not in my notes, but they're really annoying me. I'll have to fix them later when I can actually get down to it. Because remember, free body diagrams, I almost want to fix it right now. Free body diagrams are diagrams in which the forces are drawn outwards. What if I can get this to actually work nicely? It's on some kind of grid right here. Drawn outwards from the middle, right? So all these forces should be, if they're drawn correctly, if I can actually put these arrows, I'm going to move some of these things out of the way. There we go. These forces should be drawn from this middle dot here, right? Yeah, actually, I think that's as good as I'm going to get that picture. So same thing with all these other ones here, right? So there should be like a dot in the middle of this thing here. So make that a little bit smaller. Little dot there, and then all the forces should be drawn from there, right? So this is technically how it should look here. These perpendicular and parallel pieces, they're the ones that, they're the components of gravity here. So they're not really parts of the force, or they're not really there, right? But they're just parts of that force there. So I'm just going to make that like a dotted line there. You see with this dotted line here. This would be tricky to do when the arrows are all messed up. Alright, dash. Okay, cool. So all these forces should be, this is another one, should be drawn from the center, right? F applied, FG, F normal, whatever. All these forces should be coming from a center of this object here. Okay. Okay, they're all just pretty bad here. I'm just... Alright. So, my F here, you can see my Fn. I don't know why this Fn is in a weird spot there. That Fn should be up here. There. That Fn there is just to kind of balance out the gravity. So I guess it should be a little bit longer in this picture because they should be about the same length. The same thing down here. We got FF, we got FG, and what they're not drawn here is the tension, right? The tension is going to cancel out. That's in part of the Newton's third law stuff. Anyway, we should be getting to like the actual part of the question where we actually have to do the work. I'm just going to do this one last thing while I'm here. Yeah, that's just fantastic. Whoever made this picture did not make this the nicest thing in the world, did they? Nope, there you go. There should be a dot in the middle, but that's all the forces should be coming from the center. I'm going to go back and fix all these other ones later. Okay, so let's apply some of these here. So what is the average force? What is the average net force? I'm going to put that in there. Required to stop a car in 6 seconds traveling at 90 kilometers per hour. So, knowing, I'm hoping this is going to be working out pretty good for us today. Yeah, good. Knowing that F net, or A, is equal to F net over M, I could say that my F net is equal to M times my A. Right? So my average force, my F net, my mass, which I have, 1,000 kilograms, times my acceleration. Now this is one of those kind of typical questions where you're thinking, where's my acceleration? Well, it's one of those ones we have to have, it's like a two-parter. You're going to have to find your acceleration, then use that in the dynamics section. So we had to go back to the previous chapters and do a little bit of kinematics, because I don't know my acceleration, so let's put a little question mark there. I do know my time. I do know the VF, because it has to stop. Yeah, it has to stop, so VF is 0. And I know my VI is 90 kilometers per hour. I'm going to change it right away to 25 meters per second. So remember, you're just going to divide this by 3.6 there. 25 meters per second. Okay, so now we got our information here. Oh, that's a pretty easy one to find. A is equal to delta V over T. Remember, delta V is final minus initial. So we're going to have a final, 0, minus my initial, 25, divided by my 6 seconds. And I'm going to get an acceleration that's negative, because it's backwards. It's slowing us down. Well, that's fine. Makes sense. Negative 4.1666 repeating meters per second squared. Okay, so now once we have our acceleration, we can go back into our Fnet formula here. Mass times acceleration, and we're going to get a negative number. And that's also very fine because that means the force is pushing us back. That's why it's stopping us. So 4,166 times by 1,000. 666 newtons, because it's a force, but it's negative. All right. So when I put this in the proper sig digs, which we need 2 of 4.2 times 10 to the 3 newtons, I'm just going to say backwards. I'm going to give it a direction. It doesn't say what is the magnitude. It doesn't say that. So we got that. It needs a little bit more space here because the next question, part of this question says, how far does it take? All right. What's the distance it actually travels in that time as well? All right. So let's give myself a little bit more space there. So the next part of the question is, what is the D? All right. These are the kinematics questions, so we can use any of the information that we have there. We have 3 things. I could use the acceleration, but let's not. Let's just use the D is equal to, this one we don't use that often, VF plus VI divided by 2 times the time. Don't even have to rearrange it. I believe that's the formula. Let me just look up. Yep, that is the one. All right. So 25 divided by 2 times the 6 seconds. So the car moves forwards, this is all positive here, forwards 75 meters. Forwards. I know I asked for distance, but I'm going to just say this is my displacement as well. All right. What is the acceleration of a skydiver that is falling through the air? So remember, to find that acceleration, it's not just force divided by mass. Like a lot of people will just say, oh, I have 250, I'll just divide by 6.5. There's my acceleration. No, remember it is F net divided by mass. So remember, F net is the sum of all the forces acting on our skydiver. So our skydiver has 2 forces on him right now. The force of gravity, all right, also my thing's just saving all of a sudden, I hit the wrong button. And that resistance force, right? So we got our force of gravity. We have a resistance force. So our F net is going to be the sum of these 2 forces, Fg plus Fr. So remember, there's a sign convention here. So I don't know, let's just say up is positive. Usually that's the case. So that means when I do my Fg, my m times g here, which is going to be mass times gravity, 65 times 9.81. I'm assuming skydivers are pretty close to Earth. They're in the sky, but even within the atmosphere, you're still pretty close to the Earth. We're going to have a negative 637.65 newtons, a negative, plus the resistance, which is going upwards here. So we have those 2 things. So we get an overall net force of negative 387.85 newtons, which if I go back to my formula now, my net force negative 387.85 newtons divided by my mass, I'm going to get divided by 65. I'm going to get 5 point, I'm going to go 2 sig digs right away here. So, maybe I won't because I already wrote the 5. So I'll write down the sum of my numbers here. And then I'll go my 2 sig digs because the 6 is going to round up that 9 to a 10. So 6.0 meters per second squared. It was negative up there. That means it's going down here. Sweet. Remember, acceleration is always a vector. So direction is required. Okay, mass of a rocket ship develops a thrust. What's the acceleration? It's very similar to the last question. This time, I'm hoping it's going to go the other way this time, but we got this thrust upwards. It doesn't mention anything about resistance, so we'll just say Ft for thrust. We got gravity. So, similar situation. What's my F net? To find my acceleration, I'm going to need my F net. So it's Fg plus Ft. Let's just say up is positive again. So my Fg, which is equal to mass times gravity. So I'm just going to take my mass, my 100,000 there. I'm just going to type that in. 1, 2, 5, 100,000 times 9.81. So I got gravity, negative 981,000, plus this 2.5 million number here. Newtons, 2.5, there's a decimal there. All right? Plus, that was positive, the gravity is negative. That's what we get here. So here I get an overall net force of negative 1.519 million newtons. Okay. Then again, I'll just go back to my F net, or my A is equal to F net over M. So I'm going to take this number and divide it by 100,000. And I'm going to put, should show my work. I'm just going to do it anyway. Might as well, if I'm here, I might as well do it. So I divide by 100,000 kilograms. Which gives me an acceleration of positive. Oops, sorry, I don't know what. I have a negative. It's actually a positive number here. Positive 15.19 meters per second squared, which means that it's going to be 3 sig digs. So 15.2 meters per second squared. And I got pretty good so far. Okay, we got a car traveling on a level highway at a speed of 15 meters per second. Its braking force is 100 newtons, brings the car to a stop in 10 seconds. What's the mass of the car? Okay, so we're looking for mass. So in our formula, A is equal to F net over mass. Mass is then, if I rearrange the equation, times the M up, divide the A down, we get F net divided by A. So again, it's one of those questions, just like our first one on this page. We're going to have to determine, because right now, as far as I know, I just see my free body diagram here, my awesome looking car, right? Okay. Well, as far as I know right now, they only have one force here, this braking force that's stopping the car. There's no forward force, right? Because he's braking. Why is he on the gas? Bad driving habit if you keep both feet like that. So my F net is just this one force. Let's just say that way is backwards. Yeah. So we need to find the A. So I know the F net, 3,000. All right, let's find their A. So just like the last one, we're traveling along on our car, our speed of 15 meters per second. We come to a stop. I think it says there, braking force brings it to a stop in 10 seconds. That's not too bad. So my A, which is delta V over T, final minus initial, so negative 15 meters per second, 0 minus 15 gives me negative 15, divided by 10. So we get negative 1.5 meters per second squared. Okay, so now I have my acceleration. I go back to my formula. My F net, which is negative 3,000 newtons, divided by my acceleration. All right, I should probably be able to do that in my head. Yeah. Is that 2,000? Yeah. 2,000 kilograms. 2 sig digs, right? 2.0 times 10 to the 3 kilograms. Cool. I guess you could change it like megagrams if you wanted to. That's fine. All right. Find the force needed to accelerate a car up a 30-degree ramp. Rate of that. Okay. So let's do that 30-degree ramp picture here. 30 degrees, that's about that. We have our car. There's my car. It's an awesome looking car. Oh, no. It's a little block car. And we're going to have a few forces on this thing, right? We're trying to find this applied force. So I'll just call it FA, applied. There's the question mark. But the other forces we have on this thing, we got FG. We have our normal force. They don't mention anything about gravity here. Let's assume, or not gravity, sorry, friction force. But technically the friction force is in the F applied because the tire is going to turn and then you're going to push on the ground is going to push you back. So it requires friction for that. Okay, so what we need to find out in this question is what is actually pulling, just like in these free body questions up here, we got to find our F net. So what's actually pulling the car back down the hill? So we got FG, but this FG here, I'm just going to call it FGX. That's what's pulling you down the hill. And FGY here, that's going to be canceled out with the normal force because we're accelerating along the incline. We're not accelerating off the incline. So these two forces have to cancel each other out. Just logically makes sense. So my F net, because I want to find the acceleration. No, I don't. I already have the acceleration because I want to find the F applied. My F net is going to be my F applied plus that FG, just the part of FG that didn't cancel out. Like this FG, once I break it up into its red pieces, that's gone. All right. I've dealt with its components. I can just get rid of the hypotenuse number. So I don't have to worry about this FG here. This FG here I don't have to worry about. I do have to calculate it though, because I need to find those pieces. So that's going to be mass times gravity. Okay, so I'm just going to find out what that is first. Mass times gravity. What do we have here? 50 kilogram crate. Oh, I thought it was a car. It's a crate. Yeah, that makes more sense now. So 490.5 newtons. And I want to find the FGX, that bottom part in this picture. So remember that 30 degrees and this angle here are both 30 degrees. So that FGX is technically the opposite side. So opposite is sine, because I had the hypotenuse here, of that 30 degrees. So which means it's going to be half of the number, but I'm just going to type sine 30 on my calculator and get 245.25. Yeah, 25 newtons. But that's going down the hill, remember? So this is like downhill. Kind of watch out for that. Because that's going down the hill. F applies going up the hill. I need a sign convention because they're going in opposite directions. So let's say up the hill is positive here. This is going up an incline, so this is uphill. Right? So that's a positive number. Okay, so let's go back to our F net formula here. So F net, which is also equal to M times A, is equal to my F applied plus this negative number. So I'm just going to put in minus 245. So we have a mass. So I'm just going to type that in. I'm not going to show it. So 50 times 1.2, mass times acceleration. This ends up being positive 60 newtons. F applied minus 245.25. And then what I'm going to do is I'm going to add over that number. Let's just use red here to the other side. I'm just going to add that over. So plus 245.25. So I get an overall F applied of a positive 305.25 newtons. Okay, so back to my proper sig digs. Remember, a force is always a vector. So in each direction, we need 2 sig digs apparently. So 3.1 times 10 to the 2 newtons uphill. There we go. Up the incline or up the hill. Okay. Elevator is loaded at a constant rate. What's the tension in the cable? I'm thinking, okay, that's kind of weird. How come they don't give us anything? They give us this constant rate. Because the constant rate, what that means, constant velocity, it just means that my A is equal to 0. There's no change in velocity, right? Change in velocity is 0, so A has to be 0. So what's important about that is that, therefore, my F net, which is mass times acceleration, is also equal to 0. Right? Therefore, all the forces on my elevator, the tension pulling this thing upwards, and the gravity pulling this thing down, assuming those are the only two forces we have, those two forces have to be the same. One positive, one negative. They have to add up to 0. So if I were to rearrange this, I could say my Ft, if I minus that over, is equal to negative Fg. Can I find Fg? Well, Fg is mass times gravity. My mass is 1,200 times 9.81. So I get 11,772 newtons. So that means my Ft is the negative version of this number. I haven't decided is this number a positive or negative yet. So if I said up is positive, then this is a negative of a negative 11,772 newtons, which means that Ft is a positive number, which makes sense because it's upwards from the picture. So why wouldn't it be positive? So my Ft is 1,000, 1 point, how many sig digs do I need? 4 sig digs, but I have 5 right now. It's 1.177 times 10 to the 1, 2, 3, 4 newtons up. There we go. Perfect. I like those kind of questions when they, when you could be like, what's my acceleration? What really throws people off is if I said, oh, I have a constant acceleration of a number. Right? If I said it's like a number, like at a constant velocity of, and then I actually write something here of like 15.0 meters per second or something. And then be like, oh, I'll just put 15 in the A spot and like m times 15, and that's my F net. No, the A is still 0. You're just moving at 15 meters per second at a nice constant rate. So kind of watch out for that wording, right? So this is constant velocity. Because of that, A is equal to 0. Okay? Even if I throw in some kind of speed in there. Okay. We have two masses pulled on a horizontal track. What is the acceleration of the system? It's an air track, so they're trying to say that there's no friction. Find the tension between the two. Okay, so this is a good one. I like this one because it talks about Newton's third law. Okay, so let's assume that we have no friction here. The reason I moved upwards because the cursor is in the wrong spot. All right. Oh, that's nice. That line came back. No, it didn't. It disappeared on me. Let me just draw a new line. Yeah. So we have these two blocks. They are being pulled. Two are being pulled by two 4 kilogram masses are pulled by 2.5 kilogram. What is the acceleration? On a horizontal track. Well, I'm going to assume right now that the base on the wording of this question, which is horrible, I should probably redo this, is pulled by a 2.5 kilogram mass. Okay, two on a horizontal track are pulled by draped. That's how you spell draped. Draped over a pulley. No, I just move my head out of the way. Draped by a pulley. No, draped over a pulley. Pulled by a draped over a pulley. Attached to a draped over a pulley. There we go. Let's go with that. That's much. I think that's what they wanted to do in this question here. So we have these two 2.5 masses, or 4 kilogram masses. They are connected by a rope. It's going to be connected to this 2.5 kilogram mass. All right. I think that's how they wanted to reword this question. And let me just remove these numbers in here because they're going to be the way of my free body diagram. So 4 kilograms 4 kilograms. Okay. So we have this system. Looks kind of like this. We're on an air track, so we're going to ignore friction. So we're just going to start drawing our free body diagram. So on the 2.5 one, we have gravity. And we have this tension kind of pulling back upwards here, right? Because it's going to pull on the 4 kilogram box here. And the 4 kilogram box is going to pull back, right? So these two tensions here, I'm just going to call this tension A. And this is tension A as well, right? But it's a negative version of it, right? And then there's going to be, then this is going to get pulled sideways by that first block. I'll call this tension B. And then it's going to pull back on that box at tension B. So there's all our forces. Oh, not all our forces, because remember we have gravity and we have the normal force. Fn, normal force, gravity, and gravity. Okay. These, because they're on a nice level surface and the forces are not like at weird angles, they're just going to cancel each other out. Okay. So we want to find the acceleration of this system. So what we need to do that, because if I say find the acceleration of this block down here, I don't know what the tension is. So we've got to figure out a way to make the tension cancel out. So if I were to draw a bubble around all of this, I could see that all these tensions, this tension here, this tension here, this tension here, this tension here, they cancel out. This cancels out with that. This one cancels out with that. So they all start canceling out. And my F net for this specific thing here is the sum of all the forces, but there's only one force. It's this gravity down here, this mass times gravity of this 2.5 box. And that's all it is. It's just that gravity down there. It's the 2.5 kilograms times 9.81. Let's just say that way is positive. Yeah. That's positive. 9.1 newtons per kilogram. So my F net for this first part of the question, because I have to find the tensions eventually between the two 4 kilograms. The red ones I drew there. But right now, I'm just going to find the acceleration, because I'm going to have to find the acceleration first. Yep, 5, 2, 5. Okay. So we got this F net. Now the mass of this section, because I want to find the acceleration, the mass, because you have to go F net divided by mass, is going to be of the full bubble that I created there. Because since I included those forces to make sure they cancel out, I have to include the masses that are on those forces. No, the other way around. The masses that the forces are acting on. So we got 4 plus 4 plus the 2.5. So 10.5 kilograms. That's all those masses together. Okay, so we get this acceleration of 24.525 divided by this answer. We get an acceleration of 2.2 sig digs, 2.3 meters per second squared. Okay, so keeping in mind that all these numbers are my calculator. The next part of the question, I'm going to have to look at just one of these boxes because I'm looking for the tension. If I look at the whole picture, the tensions are gone. They got canceled out. How can I find them? If one's positive, one's negative, they're gone. I can't really solve for it. So I need to look at one of these smaller boxes that has just the tension in there, and just one of them, because I don't want it to cancel out. I'm going to look at the back box here. Right, I'm going to look at that box. Because this box has the FB and no other forces that I don't know. Like if I looked at the other 4 kilogram box, that tension A there, I don't know what that is. I would have to go find it. But in the second one, that back box there, there's only one tension. There's just that tension B. And that's my only tension. That's my only force that doesn't cancel out. So that's my F. So if I could find the F net here, which is equal to mass times acceleration, then I know my F tension. So what is mass times? This mass that we're using here, so this is going to be the 4 kilogram box, right? my acceleration, which we just found. It has all these decimals. I'm just going to make sure I have all those decimals written down here. 3, 5, 7, dot, 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 meters per second squared. That's equal to my tension that we're trying to find. So my tension here, I'm just going to say my magnitude of my tension. Okay. It does have a direction. I guess it's going to the right. Based on my picture, it is forwards, I guess? I don't know what you want to say. 2 sig degrees again. Cool. There we go. Okay, so two forces pull on a box. What's the F net required to keep it stationary? So I was looking for that equilibrium, that force that's going to make it stay still, right? We don't know what it is. I can kind of draw what the picture looks like, right? So this is kind of what it looks like here. So we've got this box here in the middle. We have a force that's pulling east. It just looks like it's just pulling directly east, never east. So it looks like it's going that way, 20.5 newtons. We have another force here pulling south of east. So never east, right of east, so down in this direction. Pretty steep right up there. A little bit bigger too, 32.0 newtons. And this angle here, go east then south, yeah, 67.5 degrees. Yeah. So there's going to be another force that's going to try to balance these out. So based on what I have here, kind of looks like that force might be somewhere in this northwest direction. And I don't know what it is. Right? So it might be pretty big too, because it's going to have to balance out those other two that are kind of going in the east direction. So that's what I think is going to happen. Right? Never trust your picture, trust the math. So how I would approach this question, since what I know I'm going to do is going to add these vectors together, I'm going to separate them. So I got my 20.5 Newton force here, and then I have my 32.0 Newton force here with the 67.5 degrees. What I'm going to do is I'm going to find those x and y pieces like we always do. Any sign convention, let's just say that up and to the right, north and east are both positive. Okay. And then what I'm going to do is I'm going to add these together as like a sum of my x and y's to here, just for these pieces. So I can figure out what I need to cancel them out. So that's what my equilibrium is going to be. So the first one's pretty easy. It's all going in the east direction. So it's all x and no y. This one here is a little bit trickier. I'm going to find those components. So what's my x component? What's my y component? You can see that the x component is a positive number, and my y component is a negative number. It's kind of important because we're not using standard position angles like we did in the last questions. Like if you go back to kinematics, we actually have to kind of decode, because if I use sine and cos, I'm always going to get positive numbers if the angle is less than 90. So if I go 32 sine 67.5, you can see sine is the opposite of that angle, so that ends up being the y value. So you get 29.5, 6414. Okay, I'm going to keep some decimals there because my calculator is not the best. 32 cos 67.5. So I get 12.24586 newtons. Okay, then I'm going to add those up. Add all the x's. So I get 32 point. That's a positive number. That's going to be important for later. Okay. That's a lot of decimals, so I'll keep that for now. And then I got this other number, the 29.56414. That's plus 0, so it doesn't change. So what I need now is I need to figure out what is my equilibrium. What force is required to balance this out? So what's required to make sure this ends up being 0, because this stationary means my F net is 0. That's very important here. Everything's got to add up to 0. So if this is positive 32, my other force has to have a negative 32 in it to make sure this adds up to 0. Okay? And if this is negative 29, the other one's going to be positive 29 to make sure it adds up to 0. So there's my new force, right? That's the third force I'm looking for. So what I'm going to do now is I'm going to redraw this now. I'm going to take that. I'm going to draw this picture now. So kind of like we did here. So I'm going to take this and says, we're going to go negative 8 in the x direction. So there's my negative in the x direction, 32.745-ish, right? Newtons. And then I'm going to go in my y direction. It says positive, so I'll go up. It's positive 29.964. And what I'm looking for here is what is that? What is this other force? And actually, what is this angle too? All right, so I need to find those two things. So the r, that's pretty easy. That's just Pythagorean theorem. So it's like x squared plus y squared is equal to r squared. So yeah, so take the square root of this 29.56414 number squared plus 32 point. Now watch out for the negative. You're squaring a negative is going to turn positive. So just kind of remember that. That should end up being positive. Your hypotenuse should be bigger than all your other numbers there. So let's see. We got a hypotenuse of 44.1 newtons. Okay. Then we need to figure out this angle. You're going to go tan inverse. Based on how I drew my picture, I drew my y being the opposite side. Remember, it's opposite over adjacent, so my y is my opposite. So if I just do my tan inverse of my y over my x here, 29 point. Again, don't put the negatives in. All right? You try to find a reference angle here. You don't want to find a standard position angle. I'm going to put the right numbers in the right spot. Yeah. So I get 42 degrees. 42.1. Oh, they put one decimal place in that angle there. So I'm going to put one decimal place in my angle too. Okay, so we're going to put that back up here. So 42.1 degrees. And how I drew it. Okay, so I went west first, and then I went north. All right, I went west and then north. So because of that, I'm going to go north of west. It's kind of weird because I went west-north. I wrote it last. Yeah. Cool. There's my answer. Pretty good. I like that. Let's just highlight that answer. It's in a great spot. All right, let's keep on going here. So we have circular motion and gravity. Okay, so these are fun. So I just remember in Kepler's 3 laws here, that we have the law of ellipses. I don't know why they call it the law of ellipses, but Kepler just says that the orbit of planets and celestial objects are elliptical and not perfectly circular. And they can be really circular, but they're elliptical. But we assume, for the majority of this course, we assume those to be circular because otherwise our math doesn't work out very well. Okay? The law of equal areas, which just means that as you're traveling further from the planet, because one of these, if you think about this, this is one focal point and there's another focal point. The planet, or the star, whatever you're orbiting, is one of the focal points. If you're closer to one of those, this focal point of the star, if you're closer to it, you're moving faster. All right, so this is faster. All right, and then over here, if you're further away, you're going slower. And because of that, this area that's produced here, and this area that's produced here, even though this area is longer because it's further away from the thing you're orbiting, because it's narrower, the areas just end up being the same. That's pretty cool. And then you got this little ratio, t squared over r cubed, blah, blah, blah. It just says that as long as you're orbiting the same thing, they're equal to some constant. And that constant just happens to be a bunch of our constants. The g, where it is, the g up here somewhere over here, got the g, the mass of the Earth or mass of the star or whatever you're trying to orbit, the 4 and the pi squared, there's a bunch of constants in there. And then they just happen to be equal to each other because they're orbiting the same thing. As long as you're orbiting the same thing, it works out. Newton developed this formula here too, like the Newton's universal law. Universal. I'm going to cross that word universal off now. There. Newton's law of gravitation, the capital G, that universal gravitational constant, is no longer called universal. This formula may not work for future things, so it doesn't really matter. And when we talk about satellites, the only thing keeping them in circular motion is our gravity. So our centripetal force, which is the sum of all the forces acting towards the center, you see up here, Fc is an F cent, right? This centripetal force is a net force. The sum of all the forces acting inwards. And if you only have one force acting inwards, then we're good. If we have more than one thing acting in there, then we have some problems. Okay. This formula here is just a shortcut. I don't like it because I like rearranging equations. Trying to remember shortcuts is kind of sometimes bad because you forget what the shortcut is. All right, so in this formula, this gravitational law and this gravitational field theory, where things with mass creates this gravitational field, and the Earth is creating one on the surface of the Earth. The field strength is 9.81 newtons per kilogram. As you move further and further and further away, you can see here my Fg gets smaller and smaller and smaller and smaller, right? And it kind of follows this inverse square law. Okay? You can see you can straighten the graph by going 1 over the g squared, and the graph kind of straightens out, and we can find that slope, and the slope is your g or whatever other constants might be in the question. Maybe the mass of the planet as well. So this 1 over d squared, kind of useful, because as you go further out, it decreases significantly. But it doesn't decrease to 0. Gravity's always there. You can never escape it unless you travel faster than the speed of light. Then you can do that. All right, so let's see what we have here. What else do I need to worry about this here? Net force. No, that's good. There's a few subscripts that are missing up there, but that's fine. Okay, so you got this car traveling at 40 meters per second around a 40-meter diameter racetrack. What's the car's acceleration, magnitude, and direction? Usually when we talk about centripetal force, we don't give the direction because we know it's acting towards center. But we'll just do it anyway. And when it's on the east side of the track, I guess because they're telling us where it is, we can actually say which way it's going. All right, so we're on this track that's circular. There's a circular track. We're on the east side. Here's the car. Doesn't matter which way it's going, the acceleration is going to be going inwards, so the acceleration is going to be west. Right? So it could be going this way. That could be the speed of the car, right? But my acceleration, or my FC, which would be better if I'm going to draw a free body diagram. My FC is acting inwards, which also means my AC is acting inwards. Okay, so to find that acceleration, we can find the force, but we don't have enough information to find that force. Or we just use some of the acceleration formulas. We have two choices, right? Remember our AC formulas. We can go v squared over r, or we can go 4 pi squared r over t squared. So depending on what we have, depends on which one we use. Since we have speed, I'm going to cross that one off, right? My AC here is just going to be my speed squared divided by my radius. Now, they gave us the diameter, right? They say that this track has a diameter of 400 meters. Well, my radius is half that then. So 200 meter radius. Huh? I'm not convert again. So 40 squared divided by 200, 8. So 8.0 meters per second squared. In this case, inwards would be more generic, like in towards the center. Inwards. I'm going to put the generic answer. But you can also, because of the situation, you can say it's west in this very specific situation. Okay. What's the force acting on it? So remember, force, F net, right, is equal to M times A, but I'm just going to write something else down here. AC is equal to my F net, which is FC divided by mass. So that means my FC is mass times my acceleration, which we found. Acceleration is 8, exactly 8. We got a car that's 2,000 kilograms, so I can put that information into the question. So that times 2,000, so 16,000 newtons. Again, west, if you want to put the direction in there, we can. And proper sig digs, how many do we need? 2 again, so 16 kilonewtons. I'm just going to have fun with my units now. You can go with scientific notation, 1.6 times 10 to the 4 newtons as well. Okay. A bowling ball exerts an attractive force on the pins. True, but it's going to be very small. If the mass of the bowling pins is 5 kilograms, or bowling ball is 5 kilograms, and each of the pins itself are 1 kilogram, what's the force of attraction if they're 20 meters apart? Okay, so according to Newton's law, the force of attraction, the gravitational force between them, is equal to gmm over r squared. All right, so my g, or the 6.67 number, I'll write that out in this one because I might forget. This capital G, so 6.67 times 10 to the negative 11. It's got a lot of units there, I'm not going to write them all out. We got 5 kilograms, 1 kilogram, and we get a distance of 20 meters. And got to square that. All the units are good here, so you want them to be kilograms, right? You don't want to change them accidentally to grams. That's chemistry. You don't want to change the meters to anything else. It needs to be meters. So don't need to change any of those units. So we're going to get an attractive force here of 8.3, 2 sig digs, times 10 to the negative 13 newtons. So an extremely small force, right? Not going to overcome gravity all of a sudden. Like I put a bowling pin and a bowling ball beside each other. They're not all of a sudden going to just slide towards each other. They got to push the air out of the way. There's a friction force. They can't. That's just too small. But on a large scale, with the Earth and the Sun and all that stuff, that's significant. That's pretty big. What's the magnitude of the force just before they hit? All right, so they're just saying what happens if the force is, or the distance is way smaller. So it's a similar question. It's going to be a much smaller number, right? Now I want to do this just a little bit differently. It's just like, how do they compare? Like, what is the difference between 20 meters and 1 millimeter, right? So by what factor has it changed? That's what I want to do, because that's how I'm going to do this question. I'm going to do it 2 ways. I'm going to do it both ways, but I'm going to have fun with this one. So 1 millimeter over 20 meters. What's the factor this is changed by, right? What's this? I just got a weird thing to say. I can't say it's F. I'll call it K for now. What is this scale factor? So 1 millimeter is a really small number. It's divided by 1,000. It's that number divided by 20. So I've changed by a factor of, if we go fraction, 1 over 20,000. So I'm 1/20,000th of the original distance. So what I'm going to do here, I'm going to use that information to solve this question. So what I know is my previous number was this number, right? So my new force, we do this all the time in our class, is this scale factor times r squared. So what I'm going to do is I'm going to pop this thing out of the brackets. And when I'm going to do that, I'm going to have to square it, right? So this is going to end up being a pretty big number. So it's going to be 1 over, I'm going to square this number. How do I square this? Okay, so let me do it. It's a big number. What's 20,000 squared? It is 400 million. Okay? Times r squared. So I popped that number out of the brackets, out of this square, right? So I squared the 20,000, which ends up being 400. So 1 over this number a really small number here. And then what's going to happen is that's going to flip over. Right? It's going to flip over to the other side. So because I'm dividing by a fraction, that's going to turn into, it's going to flip over, take the reciprocal of it. It's going to be 400 million times all this old information that we had before. This number here is just going to flip over to the top. It's like over 1 now. And this is all of the old information. So I could just take this, my old number, and times it by 400 million. Right? So whatever this old number was. Then you're probably thinking, why did Mr. Allen do this? No, just because, why not? Seems fun. We had a bunch of other sig digs here. So I'm just going to just quickly retype this in my calculator. So I get 3.3, this is 3.3 times 10 to the negative 4 newtons now. A significantly larger force, right? Compared to negative 13, now it's negative 4. Okay, you might be thinking, like, why did he do it that way? Like, I could have just recalculated it, right? I could have just said, okay, now, rather than doing all that, why not just recalculate this number? So I could have just said, okay, my new force here, I could have went GMM over 1 millimeter. 1 millimeter, which is really small, 1 times 10 to the negative 3 meters squared. Just done all that math again, and if I get the same number, then I just say right. I just did it a fun way. Fun way? Is it fun? I don't know. Squared, right? Hey, it ends up being the exact same number. Yeah, so that's just to confirm. It worked out. Like I could do it that way, or just recalculate it. If I could say that. What is the velocity of a satellite orbiting the Earth at a radius of above the surface, so like an altitude? So this is a big question. How much space do I give myself? Okay, not too much space. Also got to do the period of this eventually too. So in a celestial question, we got to think about. Oh, it's orbiting the Earth. Okay, so this is the Earth in the middle. So the blue little marble right here. Oh, it's going to be color. That's the Earth there. Here's my satellite. A couple of little solar panels on the side. There we go. What's holding this thing into the center is my FG. So my F cent is going to be equal to FG, right? And then we can go through our set, like what we do usually. Like F cent is equal to m times a. This mass times gravity, the gravitational field strength. Cross those off. So you'd be thinking, okay, so that's awesome. That means AC is equal to G. So wouldn't that mean that V squared over R, which is, because we're trying to find the speed, that would just be equal to 9.81. This is not on the surface, it's above the surface. So this is not 9.81, right? So not 9.81 newtons per kilogram. Right, so not that. Not that, right? We got to recalculate because we're definitely not on the surface of the planet. So we got to use this other formula. We're going to rearrange this though. Let's see what happens. So I'm going to come back to this, but it's going to be over here. It times both sides by R. That crosses off these R's and crosses off one of those R's there. So we get V squared is equal to GM over R, and then I just take the square root. Perfect. We got the mass of the Earth, that's on the formula sheet up here. We got G, that's on the formula sheet, and the radius. Oh, what is the radius? The radius, remember the definition of radius is from the center out, not from the surface out. That's above the surface. So the radius that we have to use here is the 1,500 kilometers. Okay, now we're going to do a problem. Kilometers plus the radius of the Earth, because I got to get to the center of the Earth. So it's from center to center. So 6.37 times 10 to the 6 meters. Now here's the other problem. This one's in meters. This is in kilometers. We're going to have to, if I'm going to add these together, they have to have the same unit. So this is going to be 1,500 times 10 to the 3. So we got to times by 1,000 to get into meters. I'm going to add that on to this other one. Okay. So it's like 1.5 million plus 6.3 million-ish. So it actually ends up being a pretty big change there. So 7.87 times 10 to the 6 meters. So that's my radius, right? So very important that this is above the surface, right? Okay, so we go over here now. I can type all my numbers in. 6.67 times 10 to the negative 11 times 5.97 times 10 to the 24. That's just on your formula sheet. Divided by this r we just found. Make sure you take the square root of that answer. And we're going to get something that seems reasonable. We've seen a number like this before, right? The International Space Station, which is much closer than 1,500 kilometers away, is traveling faster than this, about 7,300, 7,800, something like that. And the moon is traveling, which is much further away, at 1,000 meters per second. So it's got to be somewhere in between them. So this seems pretty reasonable, not too large. It's still fast, but it's not too large. 4 sig digs. Hey, there's my answer. Sweet. Don't have to do anything with that. Have to round it? No, don't have to round it. Really good. What is the period of this? So, similar idea. I can use this number if I want to try to solve for that, but you know what I'm going to do? I'm not going to trust that answer. So I'm going to repeat the question, but this time, rather than using the v squared over r formula, when I get to this stage here, I'm going to use the 4 pi squared r over t squared is equal to gm over r squared. That's the formula I'm going to use. So I'm going to rearrange this. I'm going to use the same r that we found from before. Same question. So same r. Let me just, I'm going to use that down here. My r is 7.87 times 10 to the 6 as well. All right. And then I'm going to rearrange this equation. So I want to get, what did I have to get to? T by itself, period. The t is in the denominator, so I'm going to have to multiply that up to both sides. So I'm going to multiply both sides, t squared, cross that. So the t squared is now on the top. So I get 4 pi squared r is equal to gmt squared over r squared. Then I'm going to take the r squareds and multiply them to both sides here. Cross that off. So now I get 4 pi squared r cubed gmt squared. And now I'm going to divide both sides by g and m. Cross off the g's, cross off the m's. Okay, so we get t squared. So we go 4 pi squared r cubed over gm. Much larger looking formula there. Now I just have to remember that t is going to have to be the square root of all of this stuff here. All right. Well, it's a lot of stuff to type in your calculator, so just make sure you square the right numbers. So we've got to square that pi. You got to make sure you cube the right number. So you got to take that 7.87 times 10 to the 6 there and cube it. And then when you divide by two things, you got to make sure they both stay on the bottom. So you either use brackets around the whole bottom piece, like from one end to the other. Use that fraction button, right? Be careful about when you divide by two things. You don't want the one number to migrate to the top by accident. And the mass of the Earth. That's the mass of the Earth, right? Yeah, and then I got to take the square root. Forgot to do that. So the period here, I'm hoping this is right, 6,952 seconds. Now, It's a big number, all right? I can't visualize that, so let's go to minutes and see what that is. So this is about 115.9 minutes. That's pretty good, actually. And then if I want to go to hours, this is like almost 2 hours, 1.93 some hours. So it doesn't really matter what units, it doesn't specify, so I'll put in minutes there. 115 minutes makes more sense to me. Cool. Okay, if the satellite has a mass, what is the force acting on that mass, right? So let's see, we got FC. So FC is equal to FG. It's probably asking for what is the net force acting on that, right? So they're looking for the FC, but the FC is just FG. Okay, that's good. So if I can find out what FG is, which is GMM over, oh, sorry, just 1 second, maybe. So let me redo that, which is mass times gravity, gravitational field strength, but that, remember, that's not 9.81. It's mass times GM over R squared. Usually we cancel out the masses. In this case, we're not. We're not going to cancel out. We're actually going to keep that mass in there. That's that number. And then this is the GM over R squared for like the previous part of the question, right? We're going to use that same radius, the 7.87, the mass of the Earth. So I can actually find out what this is. I'm going to find out what that set of brackets is there. And then I'm going to make sure I square my numbers properly. Hopefully this worked out. So the set of brackets that we have here, so obviously not 9.81. You can see it's actually quite low. It's actually 6.429 newtons per kilogram. It's a bit different than 9.81. Then I'm going to times it by, because that's going to be mass times gravity. I'm going to times it by 350 and get, oh, it's 3 sig digs now. So I'm going to have to do it this way, 2.25 times 10 to the 3 newtons. If you're traveling on a planet that's twice the mass of Earth and half the radius, what would happen to your weight? So remember FG, I'm going to assume that this is my true weight. So FG is my true weight. So that's what they're asking. You want to know what would happen to this. So we don't know what FG is, but this is my weight right now. Right? This is my current weight. I want to know what happens. What's my new weight going to be if all this other stuff happens to this? So remember, this is GM over R squared. Actually, if I were to kind of think about what we just did in the previous questions, mass times gravity. Gravity might be 9.81, right? But what I want to do here, I want to figure out, because I'm going to change these numbers, it may not be 9.1 later, it's going to be GM over R squared, right? It ends up being GMM over R squared, but we can treat it that way too. So my mass is not going to change, right? That's not going to change. So that stays constant. But this other stuff is going to change. Like the mass of the Earth is now twice as big as it was before, so this is 2m. The radius is now half of what it was before, right? So I can change that stuff inside the brackets there. So my mass doesn't change, but what I'm going to do is I'm going to pop all these numbers as much as I can out to the front, just to the front of this m here. So I'm just like, when you multiply things out, order doesn't matter. I can rearrange them however I want. So I'm going to multiply or move that 2. There's no squares or anything on that 2, so I'm just going to move that 2 out to the front. There's an m still there. There's the g, and there's the old m. Okay, and that half there, that's inside the square. I've got to make sure to square it. So if I square it, a half squared is a quarter. Okay, and then we still have the r squared. So I just kind of popped that out. So this, you can see that here, that was my current weight. So here, that's my current weight. So I can take this 2 divided by a quarter and get 8. And then this is my current weight. This is my which means 8 times the weight. Sorry about that spelling there. 8 times. Oh, I love those questions. I don't know why. Those ones just make me, I just love them. Just love those kind of questions. All right, work. So remember, work is the change of energy. I have no idea what this formula up here says. I don't know what this is all about. Work is the change of energy. Now, this is mostly incorrect. So what I'm going to do here is I'm going to cross this stuff off here. It is a scalar measurement. Work is force times distance. Right? Remember, work is the change in energy. Now, when you change energy, you don't have to just change one type of energy. You can change multiple types of energy. You can change kinetic energy. You can change potential energy. You can change all sorts of different types of energy here. So here, they were saying that work is equal to mass times gravity times height, which is wrong also. It should be mass times gravity times change in height, or it could be equal to the change of energy in kinetic energy or something like that. But no. It's equal to the change in potential and the change in kinetic, right? It's equal to both of those things. This is the work energy theorem. If I add energy to a system, it can go to lots of different places. It doesn't have to go to one thing. It can go to potential, it can go to kinetic, it can go to both, it can go to neither, it can go to chemical, or it can go somewhere. So just somewhere else. It's got to go somewhere, but it doesn't have to go to one place. Also, if there's no work being done to the system, if the energy is being conserved, if I lose energy somewhere, it's got to go somewhere else, right? It's got to be conserved somewhere else. So, in an isolated system, let me just write this down, an isolated or closed isolated system, work is equal to 0, which means that any change in potential is equal to the change in kinetic, but the other way, right? So if I lose potential, my kinetic goes up, or vice versa. Right? Let me just write this down. Oh. So this is this part of science and science. This part of physics and science 10 it's done an injustice, I would say, when your science 10 teachers teach it, because I don't know, they just glance over it. And they just don't want, because most science 10 teachers are chemistry or bio teachers. Okay. Let me just put it there for a second. Okay, power, change of energy divided by time. Oh, jeez, what is this garbage? Just get rid of this stuff here. Okay. It's the change of energy divided by time. That's it. Find the change of energy. If you have change of energy in multiple spots, add them together, divided by time. Work could also be negative, right? Something could be sapping the energy out of the system. It could be adding energy to the system, right? Because they could have those non-conservative forces. If there is a change of energy to everything, there has to be something adding energy to the system or taking it away from the system. We call those non-conservative. Gravity is a conservative force. Okay. I hope some of these questions actually, it doesn't look like they do, but let's... Yeah, I should update this. Oh, this one's not too bad. Yeah, okay. We'll figure that one out. So what do we have here? So, yeah, I don't know. I've lost my train of thought there. Okay, so we got 50 joules of energy that's done. I should probably put in the other one here. Sorry. 1/2 kx squared. That's the elastic potential energy. Okay, 50 joules of energy or work is done on a football at an angle of 30 degrees from the horizontal. So I'm assuming the force is in that same direction of that 30 degrees. It's acting over a certain distance. And they calculated this force times distance, and they got this 50 joules of energy. So it's just changing it in this direction. Assuming that also the distance is small enough, we can ignore the fact that some of the energy probably went into potential energy. but they're looking for the maximum speed, so we can assume that this work didn't change the potential energy too much. It just changed, like maybe it deformed the object and then kind of squished out, so the potential energy didn't change too much. So that this work of 50 joules is the change of energy, which is probably going to be the change in the kinetic, but not too much in the change of potential. Because we're looking for the maximum. We're probably going to say that this number here is 0. Right? So we could probably just say that this work, this 50 joules, went completely into my kinetic energy. So this joules is now change in kinetic energy. Which, remember, this is also equal to final minus initial. And most footballs are kicked at from rest, right? They're not like in the air flying through and the guy just flips up his foot and kicks like crazy. We can also assume that this is also 0, right? Which kind of makes sense. So, that means therefore this final kinetic energy is 50 joules. That's a lot of work to get to that step, right? Which you probably could have just jumped right to, but I'd like to go through the reasoning of why that is. So that means the 50 joules is equal to 1/2 mv squared, and then I can rearrange this equation. So v is equal to times the 2 up to the other side, divide by mass, so 100, 2 times 50, 100, divided by 1.2, sorry, and then take the square root. So 9.1 meters per second. Now there's a lot of decimals here, so 9.12879 meters per second. The reason I want those is because I'm going to continue using this number down the page here. What's the maximum height? What's the distance? So now this goes back to kinematics, right? So they want to determine what's the maximum height, what's the distance. So this is like a T-chart. This is all vertical though. This is horizontal. This is vertical. So we're going to use our T-chart information. In the vertical direction, acceleration is negative 9.81 meters per second squared. Our VI, not that number, right? It's a piece of that number. That piece is 30 degrees. So this number is being shot off at 30 degrees, right? So this right here is the hypotenuse. So I need to determine 30 degrees, right? Yeah, 30 degrees. I need to determine these two components, the vertical piece and the horizontal piece. So I need those two pieces, right? That's going to go over here. So sine this number, okay, so I get 4.56435. I'll just go that many sig digs for now. And horizontally, I'm going to use cos this number, right? So times cos 30. And I get 7.90596 meters per second. So remember, this is going to be cos 30 degrees. And this one here is sine. Okay, just look at that diagram that's over there. So what else do we need? We're going to need time, right? Eventually we're going to need time to solve this question. I'm going to use that information up here to find this time, because to find the distance traveled, I need my speed and my time. I just got to find that time. VF, max height, VF. Oh, max height, because we're at max height, that's 0, right? Max height, VF is equal to 0. So I have these three things. We can find both the D and the T, but in this case I'm trying to find the max height first. So I'm trying to find D. So a good D formula that involves these three things would be VF squared is equal to VI squared plus 2AD. I'm going to rearrange this. So I'll minus over the VI squared first. I'm going to then divide by 2a. All right? So we got VF squared, oops, minus VI squared divided by 2a, 2a. Okay. That should be equal to I'm just getting my number again. Okay. So I got that VF, or I got the VI. The VF is 0. 0 minus VI squared, so that's just going to be a negative number. But I'm going to divide by negative 9.81. So that's fine. Divide by 2 times 9.81. So I get distance in the air 1.30 degrees. Yeah, it doesn't seem that very high at all. Yeah, 30. Yeah, okay, 30 degrees. Okay, let me see, 2 sig digs, okay? 1.1 meters. Yeah, 30 degrees is pretty low, not a very high angle. You should have shot it way higher than that. That's fine. I'm just going to double check my math. Squared divided by 2 times 9.1. Yeah, the 1.1 meters. Okay. So there's the first answer. What is the max height? All right, so the next part of this question, I'm going to have to find the time so I can use it down here. So I'm just going to scroll this down just a bit that way. So my next part, I'm going to find t. What's my t? But now I can either find the time to the max height and then times by 2, or kind of change the question around a little bit. Rather than saying VF is 0, I could say VF is negative this number that I had before. Because it comes back down. To the same height. Most footballs do, right? Football fields are pretty flat. So, using that, I want to find time. I'm going to use the V, or A is equal to VF minus VI over T formula, delta V over T. I'm going to solve for time. There we go. So I'm minusing a negative here. Or I have a negative minus a positive. Either way, it's technically going to be twice as big as the previous numbers. So 4.56435 times by 2 essentially, or minus itself, but minus a negative of itself. So it seems like it's twice as big. And then divided by, so it's only in the air for like a second. Just less than a second. 9.305 seconds. So the reason I needed that is so I can use that all the way over here, okay, in the horizontal direction, because the ball is going to be in the air horizontally the same amount of time as in the air vertically, because why would it not be? Okay, and then I take that time, times it by the velocity. And now I get a horizontal distance of 7 point. This ball did not go very far at all. Definitely should have kicked up a bit higher than that. There's only 50 joules of energy too. Whatever. 7.4 meters in range. All right. An object has a mass and a velocity, and the kinetic energy is, if the mass and velocity is doubled, assume both of them being doubled, what's the new kinetic energy? So my old kinetic energy is 0.5 joules, and they just want to know what my new kinetic energy is going to be. And the old way, I would calculate go 1/2 mv squared, right? So my new way would be 1/2, but now I'm changing the mass to twice of what it was. I'm changing the velocity to twice what it was as well. I'm assuming it's doubled. The mass and velocity. are both doubled. I'm going to reword this question. Are both doubled? What is the new velocity? Okay. Let's go back down here. Yeah, so again, what we're going to have to do, we're going to have to move these numbers out to the front. Now the half was already there, so what I got to do is I've got to leave the half there. The half is part of the old equation, so I've got to move all these other numbers out to the front, but leave the half alone. I need the 1/2 mv squared to still be there, because that's my old number, right? This is my old number, so if I see that, that's my old number. The new numbers, the 2 and the 4 that pops out, so the 2, because the 2 squared is 4, that pops out, they're going to combine together and be 8. So, now I have 8 times my previous number. 8 times this 0.5 joules. So 0.5 times 8. That didn't work well. I don't know why I did that on my calculator. It's 4.0 joules. Or 4 joules, because it's 1 sig dig, I guess. Yeah, it's 4 joules. I just like those kind of questions. An object that's dropped from a height, what's its velocity just before I get? This is a science 10 question. Honestly, this should have been like, there's resistance on the question of this many newtons that's sucking out the energy. Find out what the final velocity is now. Like, use that information. This question is just too easy, because if gravity is the only thing, they don't mention friction. Let's assume it's frictionless. If gravity is the only thing acting on the system, it's an isolated system. Gravity is a conservative force. So that means there's no work done to the system. Right? That means the change of energy is 0. Well, then how can it gain? Oh, yeah, that's right. Because change of energy means there's change of potential and there's change of kinetic. And that's got to end up being 0. So if I lose one of them, it's got to gain the other. So it just says that if I lose my EP, then my EK is going to be the negative of that answer, or vice versa. So in this case, I'm looking for the velocity. So if I'm losing my potential in this case, so how much potential energy did I lose? Okay. Let's go put down here, or EK equal to negative EP. Okay. So how much EP did I lose? Right? So let's find that out. So the change in my EP is just going to be mass times gravity times the change in my height. So an object is, okay, oh man, now you're thinking, okay, what happened? Now I'm missing something here. I'm missing something here. No, not really. Well, that's how I would find it. Because you think, oh, I'm missing a mass. Okay, that's fine. And then the change in my EK is going to be 1/2 mvf squared minus 1/2 mvi squared. There's no way to combine those together because the square, the vi's and the vf's. So you got to kind of keep it separated. So it's final minus initial. I've got final minus initial. It's the two things. But this one's nice because you can actually combine the two together because the h is not being squared. So there's my two formulas. So what I'm going to do is I'm going to write this out. So I can say that 1/2 mvf squared minus 1/2 mvi squared, we'll talk about vi squared in a second, is equal to negative mg delta h. So what you notice is that everything has an m in it. So when I go divide by m, and I divide everything by m, you have to divide everything by m. You notice that all the m's cancel out. If one of them didn't have an m in it, you couldn't do that. You had to find the force. You had to find the mass somehow, some other way, or they had to give it to you. So what we have so far, we have this. Nope. We just said the mass cancel out. So far we have this. mvf squared minus 1/2 vi squared is equal to negative g delta h. So we don't need the mass to do the question. Another thing that we know, because it's being dropped, if the object is being dropped, I can say my vi is equal to 0. So that's important for this part. So I can say that that's 0. Gone. Right? So I have 1/2 vf squared is equal to g, negative g, delta h. Now, in the formula mgh, the g is always a positive number. Right? It's a strange thing. There's no real sign convention to energy. Change can be negative because of the change in the height. So when I do this negative and I go 9.81, I'm going to have my final, which is like 0, minus my initial, 25 meters above the ground, right? So final minus my initial, right? Assume I'm measuring from the ground up. That's what it's going to end up. I'm going to have two negatives here. So the change in the potential minus the mass, or sans the mass, is going to be 245.25. And the units are a bit messed up here because we're missing the mass, but that's fine. This is just what that number side looks like there. It's positive now, which is nice. And this is going to be 1/2 VF squared. Okay, so I'm times it by 2. You get 490 on this side now. VF squared. I guess the units would be meters squared per second squared, if you want to put that in there. And then take the square root of both sides. It's 22. All these 2 sig d questions. I'm going to have to change this worksheet. It's not my worksheet, but I'm going to have to change it. I like some of the questions. I just don't like some of the notes and the fact that everything is like 2 sig digs. Okay. One over here first, then I went down here. All right. Where are we? Oh, we're almost done, aren't we? Periodic motion, simple amount. Yeah, we're cruising along here. Where are we at? An hour 30. Jeez, taking a long time. And I still want to get over the practice test too. I'm gonna have to go home, put my kids to sleep. Okay. Maybe I'll just give you the practice test stuff tomorrow. And what did I just do? Broke it. Probably should save this before it crashes. All right, so periodic motion here. So we got some pendulums, we got some mass spring systems. Pretty simple stuff here. Actually, I don't even know if I want to go through these because I really want to get to my kids' supper here. Let's just quickly go through them. All right. So a pendulum is displaced a certain place, like this is placed vertically. How fast will it be moving when it swings past the rest position? This is just an energy question, essentially. If I displace it vertically, it's going to have to come down that much height. So there's going to be a change in potential. If I lose potential, I gain kinetics. So exactly what we just talked about in the previous question, that if I lose one type of energy, I have to gain the other type of energy, right? So this is going to be, again, it's going to be pretty much the exact same question because we don't have the mass again, but we don't need the mass, right? Things that fall because of gravity fall at the same rate. So I'm going to start off by going mass times gravity times the change of height. This is going to be assuming that it's displaced from this, and then I'm going to just say it's just let go from that rest position, from the rest position, so the VI would be 0. So when I go final minus the initial, this is going to be 0. So this is just my final EK is equal to my negative mg delta h, which is 1/2 mvf squared is equal to negative mgh. And we're going to cancel these out. Take that up here. 1/2 vf squared is equal to g times delta h. And I'll keep the square there for now. Times both sides by 2 to move the half over that side. And then take the square root of both sides. There we go. Change of height. Oh, the negative. I lost that negative. That's still there. But the change of height is negative. So 2 negatives make a positive there. So take the square, make sure to remember to take the square root. And we get a kind of a maximum, because that's how fast you'll be going at the bottom. And then it starts slowing back down, and then back again, back forth, back forth, back forth. But it's always going to be the fastest at the bottom there. So another 2 sig days, meters per second. All right. If the length of the pendulum is doubled, what would happen to its period? Another one of these awesome questions. L over G, right? L over G. I know it's just above there, but I just want to see it. So if I double it, so if I double the pendulum length, this is my old one. My new one is going to have a 2 in the L spot there. Now, doubling it, not very nice because I'm going to have to try to pop this 2 out. But I got to pop it out of the square root. Remember, if it's inside a square root, to pop it out, you just square it. If it's inside a square root, to pop it out, you just take the square root of it. So this just becomes the square root of 2 times all this other stuff. So whatever the square root of 2 is, that's my answer. So it's 1.414 times my old number. So it's going to be 1.414 times longer. There you go. What's the energy in a pendulum that has a mass of this and it passes through, and the velocity of this when it passes through its equilibrium point? So that's just saying, like, well, it's a poorly worded question. Right? What are they measuring to? Like, is there potential energy? Are they measuring to the ground? Are they saying that the equilibrium position is 0? Is that the reference point they're talking about? They don't really mention that. Let's just assume the equilibrium point is the reference. That this is the reference. So EP would be 0 at that point. So the energy, all the energy at this point would just be EK. All EK then, right? So if I go 1/2 mv squared, I find the answer. Half times the mass times the other number squared, the velocity squared, and we get a pretty small, because the mass is really small here, but 2 seconds. There we go. That's a pretty simple question. What is the direction of acceleration for the pendulum displaced from equilibrium? Well, the direction of acceleration will always be towards equilibrium, right? Just the way it is, because if I pull it to the left, the force will be going to the right. If I pull it to the right, the force will be going to the left. If I pull it down, the force is up. So the direction of acceleration is always opposite the direction of displacement, or always back towards equilibrium. Always directed towards equilibrium. Equilibrium is kind of where it wants to be. It's the middle of the graph or a pendulum. It'd be kind of just hanging down. So if I pull it off to this side, the force would be going back to that way, right? So always directed towards equilibrium. Yeah. Oh, well, that was quick. All right, we're gonna get through this. What is the spring constant of a strip of wood that following Hooke's law is compressed by blah 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 blah? All right, so there's some stuff up here about Hooke's law. And it's very important here. This formula here. No, not that formula. Oh, right up here. F is equal to negative kx. The negative part just talks about that. It's always going back. It's going to go back towards equilibrium. If I stretch it out to the left, it's going to want to go back. Right? So yeah, I'm just kind of looking at all this other stuff here. E total, E mechanical, yeah, okay. Looks okay to me. And remember, A stands for amplitude or max stretch, right, for these formulas here. And then there are some other formulas on the formula sheet that are not mentioned here about max speed and stuff. Oh, yeah, okay. So the spring constant, so if I use F is equal to Kx, if I want to find spring constant is always a positive number too. So I'm not really concerned about negatives and positives in this formula here. I divide, divide both sides by x here. We have the force. We have the stretch. In meters. So just like any other formula, we want this to always be in the proper units. So my spring constant is 180,000 newtons per meter. All right, so we've got to take that other number there, divided by 100, divided by that. So yeah, 180,000 newtons per meter. Let's put that proper sig digs. 1.8 times 10 to the 5, right? Yep, 5 newtons per meter. Yeah. It's a spring constant. There's no direction to it. It's a scalar quantity. Yeah. Shock absorbers follow Hooke's law. If the mass of the car causes an average compression of this, what is the spring constant? On each of the 4 absorbers. I'm assuming, I don't know, maybe all this is kind of distributed evenly between all 4, so we're going to have to divide the mass between all 4 tires. Yeah, as an average compression. Yeah, let's do that. Let's do spring constant for each of them. So let's say that each tire is taking an equal amount of mass here. Each tire takes equal weight. Therefore, mass could be 1,000 kilograms divided by 4. So 250 kilograms for each tire. Each shock, because there's 4 shocks. I'm assuming there's 4 tires. Yeah, 4 absorbers. Yeah, each shock. Okay, so that's going to be important. So in my picture here, we got the mass of the car on top of these absorbers. So we have a force pushing down. That's going to be gravity. And then we have this restoring force pushing back up. That's part of the Hooke's law. So that's a restoring force, right? Or the spring force, sorry. So we need to figure out what that Fr is. Right? Fr is this kind of force that's kind of pushing back up. And if this is just kind of compressed down and sits there, then Fg and Fr are both the same. They're equal to each other. No, at least the magnitudes are. Let's put the magnitudes on there. So therefore, Fr is just equal to this mass times the gravity, which is nice. It's mass 250 times 9.1. So I get 2,452.5 newtons. Okay, so now we have the Fr. Now I can go back here and I can say that Fr divided by x. I can find that spring constant. So 163,000 or 1.6 times 10 to the 5 newtons per kilogram. Okay. A mass vibrates along a frictionless horizontal surface. What is the mass's displacement if the potential energy is 4.5 joules? Okay, so they're just saying that I'm assuming this potential energy is, because it's horizontal, it's going to be our elastic potential. So that's going to be stored into the elastic using this formula, 1/2 kx squared. It's from like Hooke's law, the equation, the area under the graph, blah, blah, blah. We developed that in class. So we're just trying to find displacement, the x value. What is that, right? So we have the EP, we have the spring constant, we're just trying to find x. So if I times both sides by 2 and divide by k, I should get x squared, and then just take the square root of both sides. What do we get here? I'm kind of just cruising through these last questions because they're not the most difficult ones here. More difficult ones are the ones way back in time here. It's 0.707. Meters. in newtons per meter here. So about 70 centimeters or so. Well, you can put it in 71 centimeters or 71 centimeters because that's 7 rounds up, which makes sense. Let's fix that. 71 centimeters. I'll do that. The same mass has a max velocity of this and a maximum displacement. What is the velocity of the maximum displacement? This and this. That's a weird question. It's a maximum velocity, so that means that that's how much EK there is when there's 0 EP. Because remember, the mechanical energy of a system, the sum of all the energy of all the system, is going to be like a mix of EK and EP of all that stuff, right? So, assuming that everything obeys Hooke's law and everything's isolated here and frictionless, also assume it's frictionless, then all this EM, this initial mechanical energy that we have, is just going to be transferred between EK and EM, or EK and EP. So, when we talk about the maximum part here, the first part of this, the max has a maximum displacement or maximum velocity. Those are going to be our two things, right? So one of them is going to help us figure out what the K value is, and the other is going to help us figure out what the EM is going to be. So at the max velocity part of this, my EP is going to be 0, so my EM is just all EK. That's all it is. Okay, so how much space do I give? This is my last question. Okay, so I give lots of space here. And the second part of this, my max displacement, this is like at the very end where it has to switch directions, come back. My EK is equal to 0, so my EM is all EP, which is going to help us figure out the EK, or the K value. So the first part, let's go to the first part here. So my EM is going to be 1/2 mv squared. That same mass. Do we have a mass up here? Mass this, mass that. Maybe that's what's going to help us figure out what the mass is. Oh, no. Oh, the same mass has a relaxed velocity. Am I assuming that's the same K value? Maybe that's going to help us because I've got to figure out the mass of this object. Okay, so I'm going to use the K value from the previous question. I'm going to assume, I'm going to just draw a little arrow here. It's a weird question. I don't know if I like this question or not. All right, so let's use the K value down here. So I'm going to say the K value is 0, what was it again? Oh, 18 newtons per meter. Okay, so let's use that K value as well down there. Because I don't know what the mass is. If I knew what the mass was, I could find the EM there and go back over here and find the K value. Since I don't know that, I'm going to go the other way. So this EM is equal to this EP over here, and this EM is equal to EK over here. These both EMs are equal to each other. So essentially, I can make these two equations equal to each other. So that's what I will do. I'm going to make them equal to each other. That's how we would develop one of these formulas that are up here. So we're going to take both of these formulas here and make them equal to each other, because EM is equal to EM. Okay, so the halves I can divide or times both sides by 2, and the halves are gone. So that's good. I just want to solve for m here. So mass is equal to kx squared over v squared. And this is going to be at the max displacement. So I have the max displacement over here of 0.29 meters. So an 18 from the previous question, 18 times 0.29 meters squared divided by 0.35 meters squared. So I can find the mass to be 12.35755 kilograms. Okay, so now we know our mass. All that work just to find our mass. Now it wants us to find the velocity of this mass at very specific displacements. So my EM is not going to change, right? So it's going to stay the same. But my EM is going to be now a combination of both my EP and my EK in both these situations here. So what's both of those things? So what I got to figure out, first of all, what is the EM? So my EM, let's imagine one of these two spots, it doesn't really matter. Let's go to the kx squared one. My EM in this one, 1/2 k 0.29 meters squared. The EM of this system is going to be 1/2 times 18 times 0.29 squared is pretty small, 0.29 joules. What did I do to solve for that? So that's what I did. I took that times by 2 divided by p squared. Make sure I got the right number before. Yeah, okay. Okay, so now I know my EM. It's going to be important. Okay, I can't, for some reason, move my mouse. So I'm going to take that EM, and that EM is now going to be my EM for any point along the system. All the potential energies and kinetic energies are always going to add up to that number, assuming everything doesn't crash here. Okay, so I'm going to take that number, what we just found, and use that down here. So my EM, 0.7569 ... Let's put decimals. There are, well actually no, there's not 2 decimals. That's exactly what it is. Okay. Oh, so I just found it. Because that's my max displacement. So I found the answer. What is the velocity when it's at its max displacement? So the velocity when it's at its max displacement is velocity is equal to 0, or speed is equal to 0. At x is equal to 0.1 meter, we can go through the steps now. So EM is equal to EK plus EP. So that's its max displacement when x is equal to 0.29 meters. Because that is the max displacement. It's kind of weird. I don't know why they're asking that. Okay. But partially, not its max displacement, not at equilibrium, partially because I'm going to have a little bit of both types of energy. So both the EK, which we're trying to find, and my EP, I have kx squared, based on the numbers we have, should add up to this number. So I can find this EK using 1/2 times the 18 times the 0.1 squared. So this is 0.909 joules. So not too much is actually inside. Yep. I'm just double checking my math on this one. Not too much is in potential energy. So I'm going to minus this over. And I'm going to go minus this answer. So I got 0.6669 joules of energy inside my kinetic energy, and then I can rearrange this to solve for V. Times it by 2, get rid of the half, divide by the mass, which we found at the top there. This is a big question. It's probably why it's the last question. I don't know. And we can find that its velocity at this very specific time is 0.33 meters per second. What was the max? 3.5. So it's 3.3, so not quite there. There we go. We're done. Yay, that was 2 hours. I'm going through this thing. Sweet. Okay, so If I can, I'll try to make an answer key for that other practice exam tomorrow, Wednesday, on Sunday, so you can check over your answers. And happy studying. Bye.